Hey guys, here I am recording the vodcast for homework 3.2, and just to remind you, we're talking about homework 3.2 here. So you might remember this question from the first, one of the first questions on this past final. Remember, I'm reminding you guys about bonding because bonding is going to be a big, very important thing for thermodynamics. So I wanted to do a review on bonding before we start. So this first question says, answer the following in terms of the molecular behavior and chemical concepts. Basically answer the question. So it gives us glucose right here. And actually, I'm sorry, hexane right here, cyclohexane, and glucose right here. Identify the types of intermolecular. So let's remind ourselves, we have ionic, we have H bonding. After H bonding, we got dipole. And after dipole, we have London forces. With H bonding, we are going to see hydrogen connected to N, O, or F. So in this first one, here is an H bond, and there should be lone pairs on this oxygen here. So this thing is definitely polar with H bonding. And in cyclohexane, I see no lone pairs, and I do see H's, but they're attached to carbon. That's not an H bond. So it's non-polar, and that's going to be only London interactions. And pure glucose is going to have hydrogen bonding. All right, so let's go on to this next thing. It says glucose is soluble in water, but cyclohexane is not soluble in water. Explain. So when we think about solubility in water, we think like dissolves like. So let's write that. Like dissolves like. And we could just say that H2O and glucose both H bond. All right. So in this one, it says consider the two processes. Let's look at these two processes first. Although this process looks really weird here, all it is really doing is having a liquid turning to a gas. So this is boiling. And in boiling, heat's absorbed. That's why it's endothermic. Delta H is plus. In this one, we have actual bonds being broken right here. So turning it into the hydrogen atom and the oxygen atom. Again, it takes energy to break a bond. That's why delta H is plus in this case. Now, let's really think about what's going on. In this first case, you have two water molecules, or actually a lot of water molecules. Here, little guy. Okay. And what you're doing is you're breaking this interaction in between. That's an intermolecular attraction. Whereas in process 2, you have a water molecule and you're breaking that. That's an intra connection. So it says for each of these two processes, identify the types of inter or intra attractive forces that must be overcome for the process to occur. So for the first one, that is the inter, and the inter processes are hydrogen bonding. So hydrogen bonding, which is an inter process, is the force that must be overcome. And in process 2, it's the intra. So when you back up water to its intra, let's remind ourselves that if we think about our chart, ionic came from ionic. H bonding and dipole both came from polar covalence in terms of the intra. And London came from nonpolar. So in reality here, guys, In the first one, it was an interconnection, hydrogen bonding, and in the second one, it's an intra-connection, polar covalent. All right, let's go on to the second part here. So it says, indicate whether you agree or disagree with the statement in the box below. Support your answer with a short explanation. When water boils, H2O molecules break apart to form hydrogen molecules and oxygen molecules. We disagree. False. Boiling is a phase change. Only hydrogen bonding is affected. So what I mean by that, when you boil, you have water molecules, and the only bond that is affected is right there, the interbond. What they're talking about in this question is actually breaking this bond right here, which we know is not a possibility. So again, when water boils, H2O molecules break apart to form hydrogen molecules and oxygen molecules. Not true, false. When water boils, the intermolecular hydrogen bond is broken up to form another water molecule. It's just a phase change. All right, take care, guys.